And the expectation was that this would go to 9 gigabytes and stop. But we knew it would go to 14 gigabytes, 40 gigabytes, and keep going. This can happen, this sort of discrepancy can happen if you malloc a bunch of large things and then free them. So with this operating system and with many, when you malloc and then page into the heap or fault into the heap, that memory stays with the process until the process dies. That's why some people re-exec processes to clean up the memory space, or you use mmap, because mmap can do an munmap. We went through that gyration, but the mmap and unmap for this heavyweight workload was doing too many CPU cross-calls because of TLB cache coherency. So we did want to make this solution work where we're doing the S-break backend. So this would only really happen, I guess, if there were gigabyte-sized mallocs and frees. So another tool that we used was to profile the size of the mallocs. This one's like a Dtrace one-liner, it's very handy. So I'm looking at malloc entry, and I'm doing a distribution, power of 2 distribution plot of the requested size. And it really wasn't requesting anything bigger than about 10 megabytes. There, I've caught a 1 megabyte malloc. And we were watching this for a long time, and RSS was continuing to decline, even though it was requesting fairly small sized chunks. So there wasn't some massive malloc and free cycle like I guessed. So the next question was, why is the heap growing? Why is the heap continuing to grow even though we're not really requesting a lot of data? So another tool that's really handy to have, being able to trace why the breakpointer is expanding. Dtrace, that's easy. If system type works for you, I'm sure this is easy as well, where you can detrace that particular system call that moves the heap breakpointer, and then look at the entire user lane stack backtrace. This is great because in the top of it, I have libumem, and I can see the internals of the libumem allocator, and then down I can see into the application. And so we've got eleveldb was running, you can see the C++ mangled symbols, and then beam.smp for the Erlang VM. So libumem will explain why the allocator is deciding to extend break, and then beneath that you'll see why the application is requesting memory. So you get a lot of pieces of the puzzle here, so you get some good idea of why that was happening, but it didn't really explain it. Like, we looked at the stack backtraces and we're like, it just looks normal. It just looks like a normal requested memory. It's not anything terribly unusual. I used Dtrace to look at the size of the mallocs that were ultimately causing the breaks, and they were 8 megabytes or 10 megabytes. But the heap kept growing, even though it looked like there were 6 gigabytes available, 10 gigabytes available, 20 gigabytes available of unused space in the heap. It kept growing based on these in comparison, small allocations. This was actually starting to look like an operating system issue. This was starting to look like fragmentation in libumem. So more tools were created. I never thought I'd get this deep inside libumem, and so hadn't really looked at the code before and started using Dtrace to examine it. Wrote some scripts to look at memory entropy. So it has some great functions, so you can actually track the malloc size and the free size. And I wrote a script to print that out every 60 seconds with the heap growth. And I confirmed that the malloc and frees over time did cancel each other out, yet we were growing the heap. We were growing RSS, resident set size, which really smelled like fragmentation. Then used Dtrace to look at the code path taken for allocations. Why is libumem, why when given an 8 megabyte malloc and you have 20 gigabytes available, are you still extending the heap? Looked at allocator internals, the sizes that were being used inside it, the options, the flags. This was done in a production environment, briefly. Tracing frequent things does come at some overhead, and these were very frequent allocs. So I would often trace for 1 second or 10 seconds only and then get enough data to go and analyze. But it was casting rays of light into what was a black box. That's just like some of the output I was digging over where I was doing a Dtrace flow indent, looking inside libumem. I can see the column shows data like That's the UMEM oversize segment, then it goes into sbreak heap and sbreak top, printing out flags from all the arguments to vmem xalloc and the return value, printing out stack backtraces. So I had a lot of information, and eventually found it was the InstantFit default behavior of libumem that was causing the growth. Someone had suggested this to me earlier, but I wasn't looking in the right place. After looking at it with Dtrace and looking through the internals, it's like, yes, I'm actually in the InstantFit code path. We built a libumem version that forced the use of VM bestfit. And so this allocator actually has different options. If you're into memory allocators, they normally do. They've got things like first fit, best fit, next fit, fast fit, instant fit, as it turned out. Instant fit was trying to allocate as quickly as it could without trying to find the best place, and it was leading to this massive fragmentation. And so my colleague Robert made this as a tunable so that we can set it. It wasn't tunable by default, which is one reason why we never found this through experimentation. Customer restarted React with the libumem version, problem solved. So it was actually an operating system allocator issue. That's the first operating system really bad allocator issue I've had. I've had problems with operating system allocators before. On the cloud, so just to throw some more data out there, with OS virtualization, you can have paging without scanning. And so paging is where you're swapping blocks of physical storage. I don't mean swapping where you're moving entire threads. Resource control paging is unrelated to the page scanner, so VM stat scan rate doesn't kick in, even though you're doing anonymous paging, which makes it pretty confusing. This is in some ways the best part, but also some of the confusing parts of using operating system virtualization versus hardware virtualization. With operating system virtualization, you just have one kernel and you're creating zones, or in FreeBSD they call them jails, whereas with hardware virtualization, you're running multiple kernels. And with multiple kernels, when you run out of memory, you go through the normal code paths. You're going to do scanning and you're going to do whatever normal tools tell you. With operating system virtualization, there's only one kernel that's managing all of system memory. And then each of those zones is managed through a secondary process. So it used to be RCAPD, but that was changed. And so that's also confusing because customers have learned the standard operating system ways that memory pressure happens and performance impact happens. But in this environment, since there's new resource control methods applied, those standard metrics don't really work. And so they need new things to look at. And we've been rolling lots of new tools. I mean, that's one lesson we've learned, is that anytime you apply a new method of resource control, you need to let the customer know that it kicked in and that it was doing something. Just like we normally look for memory pressure with scan rate or whatever. So summarizing that problem, with memory, there is superficial data available. You can always look at processes, resident set size, you can dump out the memory map. Detailed information is not normally available by default. There are various memory heap profilers out there that come with different degrees of overhead to run. libumem, as far as I know, is one of the best because of the design. Many new tools were created to work this problem. Not easy, were made possible with Dtrace. A disk issue, just one. Application performance issues. Disks look busy, according to IStat, so we should blame the disks. In this example, I've just got 50, 60% busy. Many graphical tools out there are built upon IStat, so you may be using this form of data without really realizing it. Disk on the cloud, tenants can't see each other. So this really highlights a problem with looking at metrics in your virtualized instance. Maybe a neighbor is doing a backup, and maybe that's railing the disk, and maybe that's hurting me. Maybe a neighbor is running a benchmark. That's actually too close to the truth. That was before we implemented CFS IO throttling so that we could actually throttle tenants. Because benchmarks, a lot of benchmarks stress test the system, and they can be the worst tenants to have. So they'll push resources to their limit. If you're in a tenant, you're in some virtualized OS, you can't see the other guy. You can't see the other guy running a backup process. You can't see the other guy running IOZone or Bonnie or whatever, because you can only see yourself. So there is a tendency to blame what you can't see, or suspect what you can't see. In reality, disk, applications don't talk to disks directly usually, unless you're doing some sort of direct I/O. Applications talk to file systems, and they're hurt by file system latency, not disk latency. Disk I/O as a metric can be unrelated to the application. Asynchronous tasks, inflated from what the application has requested. Application requests one thing, the disk does a lot more. Deflated, and also blind to issues caused higher up the stack that are affecting applications. Disk issues with I/O stack. So, for example, unrelated. You have other applications and tenants that are doing disk I/O, and their disk I/O is slow. When you run I/O stack, you see that, but it's not you, it's not hurting you. It's someone else. File system prefetch is also unrelated. You might see the disk's doing a lot of reads. It's just prefetch. You didn't request that. The file system's trying to be smart. File system dirty data flushing. This is a common one when CFS was first released. Why did the disks go to 100% busy every 30 seconds? It's like, well, that's a ZFS transaction group flush. It's just flushing out writes. Your application is not waiting on those writes. Don't worry about it. I guess a flaw with I/O stack was it didn't split out the service time for reads and writes, so you could easily see that. Disk issues can be inflated, or I/O can be inflated. So my application does 10 byte writes, but it gets rounded up to the next record size in the file system. Might be 128K. There's extra metadata for the on-disk format, and you may have the read modify write cycle of RAID 5. Things can get deflated, so read caching. The application is doing a whole heap of reads, but we're just bouncing out of main memory. And write buffering. And issues can also be blind to, if you're looking at the disk metrics, you may be blind to various issues that are hurting lock contention in the file system. CPU usage by the file system, I only hit this one recently when we had a customer complain about 20 to 30 millisecond I/O. And there was no I/O stat that corresponded to the I/O. The disks are idle, why am I doing 20 to 30 milliseconds? I'm like, oh, this is a ZFS lock issue. Let me go and aim Dtrace at the kernel, and I'm using those flame graphs, and it's just doing normal work. It's only then did I think, oh, I'm an idiot, I should trace the characteristics. It was an application, due to a defect, was doing 30 megabyte reads. Which just, normally it's doing 30 byte reads, but all of a sudden we do 30 megabyte reads. It can take 20 milliseconds to do a 30 megabyte read, even though you're getting it from main memory, to do whatever B copies are necessary to create the data structures. So, that's a new one that I've added to my list. File system software bugs do happen. File systems are software. You have various queues inside the file system that can also add latency. You won't see that from the disk, depending on where the queue is. Disk cache flush latency, if your file system does it, like CFS does. CFS does proper SCSI disk cache flush commands so that it can make sure its transaction groups are properly flushed out. They don't show up in ISTAT. ISTAT only shows reads and writes. It's not showing your cache flush latency, even though your application may be waiting on that because it's doing a synchronous write. So you're blind to that type of issue. And also, file system I/O throttling latency for multi-tenant environments, which we've added for ZFS. So we've been using Dtrace to solve this particular problem. And the problem is we would like to show file system latency to the customer, not disk latency, because it's the file system that your thread is waiting on, that your thread will block on when it's doing a read or a write, and then wake up sometime later. It's a one-liner with Dtrace. There, for an example, I'm doing ZFS read entry to return. And you can see a nice spike for cache reads between 4 and 30 microseconds. And then our disk reads are between 4 and 16 milliseconds. Another favorite tool of mine, ZFS Slow, which I put in the Dtrace book. This takes a millisecond argument, so I can say, I just care about file system I/O that was longer than 10 milliseconds. So the customer's complaining about slow I/O, so cut out all the fast stuff, just show me the really slow guys. And instead of summarizing, it gives me a trace.